Okay, guys, can you hear me?
Yes, sir.
Yes,
Good afternoon, sir.
Yes, sir.
Okay,
yes,
yeah.
sir.
Yes, sir.
Yes, sir.
Okay. Good morning. Okay, so let's start. So, yeah. Mm, yeah, so today we'll introduce one of the core concepts in statistics, which is known as random variable. In fact, from now onwards, whatever we'll be discussing or we'll be defining, everything will be in terms of random variables. And you'll see gradually we'll forget all about sigma algebra, this event, this and that, to the probability space, because we'll assume that there is an underlying probability space, and we are defining all the concept, okay, on top of it. Like we have a sample space, we have a sigma algebra, we have a probability measure, and then we are introducing all these concepts. Okay, so first of all, what is the need of this idea and what is it? Random variables. So we'll discuss different kinds of random variables. So let us first introduce why do we need them. So the idea here is in many random experiments, the elements of the sample space, the elements of the sample space did not be numbers. Okay. And for example, if you just toss a coin, for example, tossing a coin, let's say, tossing a coin. So the sample space is head and tails, and they are not numbers, right? Head and tail. In fact, if you do any kind of analysis of data, data can arise from many contexts. For example, you want to analyze, as we said before, like all the tweets, okay, or some specific tweets. And tweets are not numbers; they are written in languages. So let's say in English. So then you have to mathematicize it, meaning you have to produce some numerical values associated with those sample points. For example, head and tail, you need to mathematize it. And in general, what happens is if you have a large amount of data, then that will be really crucial. Like how do you define numbers? How do you associate numbers with the sample points, which are not numbers? So the idea, the reason of this concept is basically mathematize the outcomes. Mathematize the outcomes. Okay, this is the idea. Now, why we are saying it mathematize? Because if we are dealing with numbers, we have our whole understanding of mathematics. We can play with numbers. Okay, we can define sequence, series, continuous function, differentiable function, derivative, this and that. So we can have a whole lot of literature based on numbers. Okay, and which could be difficult if you just use some particular language, some words, some letters, alphabets. Okay, that could be difficult. So in fact, you will see this is very fundamental in all branches of engineering and science. That, for example, so the idea of computing, everything, like even when you type something on your keyboard, okay? So in the screen, this is displayed as whatever you are writing. Let's say you are writing a letter, you are writing an email, okay? But the process of this information, what we are writing on the computer, because computer is a machine, it does not understand, like whether it is A, whether it is B, it does not understand that. But it is displaying this because there is a mechanism. There is a mechanism which translates these alphabets into numbers, and those numbers are stored in our system, and that is how it is displaying. Like, for example, in terms of information, the original idea of processing of information, how to process information, for example, okay, that was due to Claude Shannon, and he like that was in 1948. So in fact, he is known as the father of information theory. I mean, due to him, we are doing everything today. So he defined, okay, he first said like if you have a source, information source, that has to be treated as a random variable. Because, for example, if you're writing emails, so you are just writing some bunch of letters, some bunch of alphabets, let's say, okay, but they are not random. If whatever you are writing, it's a sentence, it's a word, the number, the alphabets, whatever you are writing, they are not randomly put together, right? So there is a meaning to each word. There's a meaning to each sentence. So they are not randomly put. So the way that is coming, so we may possibly attach some probability to each of these letters, for example, and then so then we can define a random variable. So his idea was, okay, first of all, information source has to be a random variable, and we have to digitalize information, meaning we have to, when we are processing this alphabets or whatever, the random variable, okay, whatever based on, I mean, whatever I will define it, what will be the sample space. Okay, so let sample space could be some bunch of letters or all letters, that's all alphabets. Then each alphabet has to be encoded with a sequence of 0, 1. So that means we have to digitalize it, okay? And sequence of 0, 1 in then, okay, encoded in our system as, let's say, some voltage of some transmitter, okay? So the voltage is low or high, based on that we have 0 and 1. So once you have in memory, so a sequence of 0 or 1s or a string of 0, 1s, so that will define a particular letter, and that is how computer understands what is that letter. So the fundamental concept behind science and engineering, okay, is the idea of digitalization when you talk about computing or processing information. But in general, whenever you want to deal with the data, okay, so we have all the machinery based on numbers. And if our data points are not numbers, then the idea would be we have to associate numbers to the data points. Okay, and then we can use our whole machinery of numbers and interpret or analyze some kind of a data. Okay, so now I'll define. So the goal is, so this is the motivation: mathematizing the sample points, our possible outcomes. Okay, we have when we associate numbers with the sample points. If those are already numbers, that is also fine. If they are not numbers, then we can associate some numbers. Even if they are numbers, then also we can introduce some new number. So the process goes on basically. Okay. Okay. So let me just define what is it. The definition of a random variable. So suppose since we are defining first time, so let us recall. So we have a sample space S. Okay. Then we say a random variable. A random variable X, let's say, is a function. Is a function from the sample space S into the set of real numbers. The set of real numbers. I will denote the set of real numbers as R. This is not IR. This is one line R and then R. Okay, one vertical line R, one vertical line and then R. It is a standard notation for set of real numbers. So, for example, if you just write R, okay, that you can also denote that this is a set of real numbers. Okay, this is the set of real numbers. You can of course denote it like that. But whenever this kind of R is written, you already have to interpret it like this is the set of real numbers. This is standard notation in mathematics. Okay, that this is the set of real numbers. So we'll always write R like this: one vertical line and then R. Okay. So this is a function first of all. So we can write it like a function. So S to R. So now we can see if we have a sample space, so we are associating a number with it using this function. Okay. Such that this is not any function, such that for each interval, okay, let's say I, it could be close, open, whatever. I'll come to that. I in R, the set of all sample points such that the value of this function x at s is equal to, it belongs to I, okay, is an event. In fact, because of this condition, we need that set of all events to be a sigma algebra. I'll not discuss that, but if you just want to think about it, you can just find it out that why do you need a sigma algebra structure in the set of all events? Event in S. So if you want to see it pictorially, then what is happening here? So let's say this is my sample space S. There's something here. These are the possible outcomes, and this is the set of all real numbers. So there we have zero. We have zero here towards plus infinity, here towards minus infinity. Okay, this is infinitely extended. Then what we are doing here is we are associating some numbers. Okay, third number. You can assign same numbers also to different possible outcomes. Doesn't matter. It is just a function. Even you can consider constant function also can be a random variable. Okay, I mean in principle according to the definition, but whenever you want to analyze data, then that will not be much meaningful. Okay, because data points are different and you are assigning the same value, so then that is not that much meaningful depending on the context. So basically what you are doing is you are assigning all these numbers, okay, through this function x. Now even means what? Even and this has the property. So if you take an interval, like say here, interval means it is like, let's say AB. Okay, this is an open interval. So what is AB? Open interval AB. This is set of all real numbers such that x is bigger than A and less than B. Okay, you can have other intervals as well, like open, like closed interval AB, which means set of all real number x are such that A less equal to x less equal to B. You can also have one side open, one side closed, and so on. Okay. So that means what is happening if I take any interval here on the real line, and like here, then the set of points, okay, whose value, for example, here there is only one sample point which is taking the value inside this AB. So that means in some sense this S, so let's say this is X, then the corresponding, so then X must be an event. This is the way you have to define the event. So, or let's say the function. So in function has to satisfy this property. Like whatever interval you take on the real line, the values, the sample points, which will take values inside that interval, that has to be an event. Okay. Of course, if you take all subsets, for example, if you have a finite sample space, and of course you can also consider like all subsets of S as events. Then this condition is this condition is trivially satisfied. Because whatever interval you take doesn't matter. If you go back to the sample space, of course you'll get a subset, and it is always an event. It doesn't matter. So that has to be keep in mind. Okay, that when you are defining this function, this or sometimes you can say x inverse, but I will not use the word inverse because this function need not be invertible. Okay, inverse in that sense, the pre-image. So if you take x, y, z, whatever the sample points are, x of, or let's say s1, s2, and s3, so on. So x of si, let's say, so the image of some sample point is some real number. Then if you take the real number, then you can associate the sample point as a pre-image of that. Okay, that also you can say. So whenever you take an interval, if you take the pre-image of those the real numbers, okay, in the sample space, then that has to be a subset of the sample space, of course, and that has to be an event. This is the only condition that needs to be satisfied. Okay. Okay. Now here, so I want to just make a point here. This is remark because in many occasions, like in comprehensive viva and this and that, in exams, people ask this question: what is random variable? Okay, and some people always answer. Some students always answer that this is a variable which is random. But you have to keep in mind this is not a variable. Random variable is not a variable, and it is nothing randomness about it, and it is not random. Not a variable, and it is not random. Okay, so it is just a function. That's why other day I said this is inappropriately named, wrongly named, you can say. Okay, it is not a variable, it is not random, it is just a function. Simply, it is a function. Okay, so any random variable is what you are associating numbers with the sample points, and that function which does this job is called a random variable. And since this set in the right hand side R, it is uncountable. Okay, of course S can be finite. Okay, S can be just the sample space. You can have only finitely possible outcomes. So this map, okay, need not be a 1-1 map, need not be a bijective map. Okay, whatever numbers you want to assume, you can actually assume. Based on that, you can do your analysis. And you, depending on the problem, you have to actually define this random variable. How do you associate the numbers? This is itself a problem. Okay, how do you define your random variable in order to interpret your data? In order to interpret your data means in order to find the association of numbers with your data. Okay.
Sir,
okay, we'll see some examples. Yes.
Sir, how a randomization function work in computer, sir?
How?
How a randomization function, sir, that you have discussed this function, sir? How it will work in computer, sir? Mathematical algorithm, sir, I am just asking.
How do you work means in what sense? Like that thing I explained?
Means, sir, how this works, sir?
I didn't understand your question.
Means, sir, when we are
How
calling
which works?
Means, sir, some it will take some random value, sir. I am asking.
No, it will not take random value. You have to assign these values. So so for example, here you have to define the random variable. For example, let us discuss an example. So suppose we have some 2's. In fact, there is some number. Let's say I was talking about an example last day. So let's say the colors of mango. Okay, what are the possible colors you can assign with mango? Okay, you can say green. Okay, I'll give you a lot of examples, but let us pick this example. Green. You can say if it is rotten, it could be black. Okay, it could be yellows. You can assign different colors. Okay, it could be reddish or red. It could be sometimes pink as well. So you can define this color. So let's say these are my sample points. Okay, now whenever you want to analyze the data, like if you have, let's say 50 samples, so you have 50 mangoes, let's say. Now you have to associate, you have to classify which one is green, which one is black, which one is yellow, which one is red, based on certain parameters, let's say. Okay, then you have to assign the function. Let's say by green, I mean, let's say 1. By black, I mean, let's say 2. This yellow means 3, red means 4. Then that will be a random variable here. X. So X of green is 1, X of black is 2, X of yellow is 3, X of red is 4, and so on. You can define it otherwise. Instead of green to be 1, you can define green to be 2, green to be 3. Then that is another random variable. Okay, I'll come to that. I'll give you a lot of examples. So in computer, so in computer, how it works means you have to first define the random variable. You have to assign these values. And then whatever, so because computer can process numbers, okay, or all your algorithms deal with numbers, you can of course do the natural language processing, you can do that, but ultimately end of the day, you have to write, you have to assign some numbers. That could be binary numbers or whatever numbers, or string of numbers, whatever it is. So you have to assign some numbers, okay, with this thing, with your data. Okay. So yeah.
That means according to our convenience, we can set green and black both to 1.
Yeah, you can define. Yeah, you can do that. But if you do it, for example, green you can assign 2, black also you can assign 2. Then when the data comes into your hand, you cannot distinguish green and black.
Yeah. That means, if we have to do something like, if according to our convenience, we can do that also.
Yes. So this function need not be one. It could be any function. Only property is that this has to be satisfied. Even some people will not even include this. They will assume that it will satisfy. But I want to mention here, because I have to also tell you what is the importance of the sigma algebra. Why did we consider actually all possible events have to be of this particular form? In fact, you didn't ask this question, but let me just say, let's say 1, 2. This is an interval. And you can also take some, let's say -1, half, 1.5, let's say. That is also an interval. And there is inside, there is some common points, which are both here, okay, in both this, let's say this interval I1 and this interval I2. Okay, they are both here. Now, when you take the pre-image, okay, in that intersection, what happens to that? So that will be a subset of both. So that will be the intersection of the corresponding events here. So the inverse image of pre-image of I1 and pre-image of I2. So the intersection of these two events also, okay, has to be an event. Okay, so that's why it has to be a sigma algebra. Okay, so you can just think about it. I'll not spend that much time on this. Okay, but you can think about it, and then you'll find out why you need a sigma algebra structure. Okay, in the beginning, why did we talk about sigma algebra structure? Okay, let me give you some more examples. So let's say, as I started with, it could be head and tail. Let's say, okay, tossing of coin in this experiment. Tossing of coin. Now, for example, you can assign this value x of head, okay, is equal to 0, x of tail, okay, is equal to 1. Or here, for example, in this example, x of green is equal to 1, x of black is equal to 2, x of yellow is equal to 3, x of red is equal to 4. So basically, what we are saying here is, whenever we are defining random variable, the range of this function is also important. Okay. In fact, based on the range set of this function, we will classify random variables into different types. Okay. So let me just define what is called the sometimes it is also called the space, or just the range space, or just the space. Okay, this is another definition. Nothing but the range set of this function. Okay, the space, or you can say the range space. It is just the range of this function, range set of this function. The range space of the random variable, or of a random variable, okay, x, let's say from S to R, is this. All such this real numbers such that x is equal to xs for some s. For some s. That means what we are saying, if you want to look at this pictorially, so I have some sample spaces, there are different points. So then I have this real 9. And whatever way I assign these values doesn't matter. So ultimately, I'll collect all these values and will form a set, and that set is my range set, or just a space of the random variable. Okay, this is just a set. Okay, and we'll denote it as Rx. Let's say the range of x. This is the notation. Let's say we'll denote it like Rx. This is the notation for the range set, or the range space, or just the space of the random variable. Okay, so in this case, the range set is just 0, 1. You could have defined it other way also. You could have defined 3 or 4. Okay, but now this is the beauty of this thing. If 0 is not equal to 1, okay, and you could have also assigned 1 for head and 0 for tail, 3 for head, 4 for tail. But whatever way you define doesn't matter. When you are analyzing the data, it has to be independent of this random variable, right? In some sense. So when you are translating it into numbers, so that means whether I give it a 0, 1 or 1, 0 does not matter. Okay, that when you are analyzing this data or analyzing this random experiment, okay, that has to give the same interpretation, same analysis for different random variables, having some properties. Like if I take both head to be equal to 1 and tail also to be equal to 1, then that is a different kind of a random variable, because that cannot distinguish head and tail in that case. Okay, so then I would say that, okay, you can define x of h to be 3 and x of tail also to be 3. But that also then it has to be invariant, so it doesn't matter whatever you define the random variable. Okay. Okay, now let me give you some more examples and calculate the range space. We have to understand this is very, very fundamental. Okay, so consider an experiment. Let's say, so toss a coin. Let's say 10 times. Okay. Now, what is the sample space here? How many elements are there in the sample space?
8 and 10, sir.
Yeah, what is the sample space here? This is a set. So that, yeah, so sample space is like this. So let's say S1, S2, dot, S10, okay, perform one time, and then SI, okay, should be head or tail. This is my, so it's a sequence, okay? It's a sequence of length 10 of head and tails. Sequence of 10 heads or tails, okay? So I mean sequence of 10 items, and items are only head or tail. So what is the number of sample points here? This is 2 to the power 10. 2 to the power. Right? So this is sample space. Now suppose we want to define a random variable on this. Random variable, S2R. So you want to assign some real number to each of these possible outcomes, I mean each of the sequence. Okay, suppose I am interested to know about how, I mean I am interested to analyze about heads, appearance of heads after performing this experiment for a long time, let's say. Okay, then I can possibly define this function, okay, x of s, and this s is a sequence of 10 heads or tail. This is, let's say, to be equal to number of let's say a number of heads. You could have defined also number of tails, doesn't matter, in the sequence s. Then this is my random variable. Then that means if I take suppose something like h, so therefore this is the sequence, okay, ht. Then what is the value of this sequence? 1, 2, 3, 4, 5. The value is 5. Okay. So what could be the possible range set? Possible range set could be a subset of this. In fact, here it will be up to 0, 1, 2, up to 10. It is a subset of. It is a subset of R, proper subset of R. Right? It is just a subset of this real number, and here it could be 0 up to 10. Because we are interested about the occurrence of heads, let's say. So how many times I am defining it to be a number of heads. You could have defined also number of tails, doesn't matter. So one thing we also have to notice here that based on the context, depending on the context, you have to define random variable. And this, when I'm interpreting random variable in a true sense, okay, in a physical reality, then I am trying to measure something. I'm assigning a value to a sample point. That means I'm trying to measure something. Like here is number of heads. Okay, suppose instead of this coin, okay, instead of this coin, if it is a die, then I can also say, okay, sum of these outcomes. I could also say product of this out. Whatever way I can define my random variable, I can define, and then I can try to analyze whatever my context is. Based on the problem, I can analyze that. Okay, so it is basically measuring something about the sample point. Okay. Now let me introduce a notation which you'll be using throughout this course. Okay, this is an important notation. So what we said is, this is my sample space. And then we are assigning, and this is the real line. This is 0. This is the real line. Let's say I pick any point here, whatever way I pick. Let's say I pick some x. So then there can be some sample points. This is my random variable. Let's say x. The function is defined from s to r. Corresponding to this x, this x could be any real number. It could be root 2 pi e 3 100, whatever we want. Okay, for any such x, the small x, any such small x, there may or may not exist some sample points which are mapped to x. Okay, so I'll define this. I'll write this notation: x is equal to x. This is my notation, and then I'll put a first bracket here. And this notation, it means set of all sample point for which it assigns the value x. So it is a subset here. All of these values are assigned to x. If no sample point is mapped to x, then this is an empty set. It is a null set. And this is always a subset. Okay. And this is always an event. Okay. So by this, I am declaring this to be an event. So that's why we need null set also as an event. So this event x equal to small x, capital X equal to small x, it means set of all sample points here, set of all sample points which are mapped to x. For that, I'll use this notation. So for that, I'll use this notation. In the first bracket, x equal to x. Now, instead of this, okay, why it is an event? Because of my definition. I'll come to that. Because instead of this x equal to x, I will also write, I'll also write a less than x less than b. I can also write less equal to, I'll come to that. Then I can write this as bracket. And then I'll define this to be all such numbers s such that x of s is lying between a to b. So this entire event, according to the definition, this will be an event. Okay, because definition said whatever interval you would take from the right hand side, when I defined here, whatever interval you take here, whatever interval you take, all the pre-image of some of this, okay, that means all the sample points which are mapped inside this interval, that has to be an event. So this is a part of my definition. Okay, so this has to be an event. This has to be an event, and it is denoted as this, that a less than x less than b. Similarly, I can include some less equal to, then this will be less equal to. Here also I can use less equal to, then it will be less equal to. This is also an interval. And x equal to x itself is an interval because you can say xs, okay, you can say these are all points which are bigger equal to x and less equal to x. Okay, so a and b, if they are equal, a and b, they are equal, let's say they are equal to the a equal to b, then it will be just x equal to that number a. Or here I'll write x equal to the small x, capital X equal to small x. Okay, so that is also an interval. Okay, no, a trivial interval. So this is my notation. Throughout we'll be using this. So if you want to see it pictorially, what is happening? I have this sample space S, and then I have this real line, and then I take any interval here. Let's say this is my interval a to b. Then this set, okay, there's a set of all sample points which are mapped here. All this mapped here. Okay, that has to be an event through X. And if there is no sample point which are mapped here, then this set, this subset is a null set, and null set is always an event. Okay. And based on this range set, I'll classify random variables. So random variables can be, let's say, of three types. Random variables. This is also called discrete, continuous, and mixed. So in the syllabus, we have only discrete and continuous. So what are these? Let me just define what is discrete. If, so let us say x is a random variable, and if Rx, that is the range set or the space, okay, of the random variable, range set of x, okay, is countable, then we call the random variable x a discrete random variable. Now see here, there is an interesting thing. My sample point, number of sample points could be uncountable. It need not be discrete, because sample space is discrete means the number of points in the sample space is countable. Here what I am assuming is discrete random variable, meaning range set of the random variable is countable. Okay, so if the sample space that is discrete, of course it is always discrete. The corresponding random variable is always discrete, because if this set is countable, then when you map into R, then you can get only countable many points. Okay, so then that is of course a discrete random variable. But even if you have uncountable sample space here, let's say it is a constant function, then you get only one value in the range set. So then the corresponding random variable is discrete, but the domain is continuous. Okay, that can also happen. Okay, so so the range set, okay, the range set, if the range set is countable, then we say it is a discrete variable. Otherwise, let's say we call it continuous. We'll come to that later. We'll define it later, because first we'll discuss about discrete random variables. We'll come to that. And let us say if it is not countable, it is called a continuous random variable. We'll come to that a little later. But let us first discuss what is a discrete properties of, what examples of discrete random variable. Discrete random variable. So what is a discrete random variable? So random variable is x, which is from S to R. And this set R of S, which is equal to all such sample points, all such x, real numbers, all such real numbers, such that there is a sample point for which it has in this value for some sample point. Okay, this is my range set of this x as a function. And if this is countable, this part Rx is countable, then we say it is a discrete random variable. Now, in order to characterize different kind of, so what is happening here now? So let me say what is happening here now. We started with an experiment. We said, okay, we have a random experiment, then we have a sample space, then we are defining what is called a random variable. But what is my goal? My goal is calculate probability of an event. Okay. Now, how events are linked or connected to random variable? This is the way it is connected. This is the way it is connected. So that means if I want to calculate probability of an event, I have to interpret this event in terms of the corresponding random variable, and then I'll calculate its probability. Okay, so event from now onwards, okay, it's of course a subset of the sample space, but always the event corresponds to the random variable whenever I have a random variable in the scenario. So whatever we'll be discussing from here onwards, once we have a random variable, all the events then can also be explained in terms of the random variable. They are the pre-image of some subsets of the intervals of R, okay, through X, through the random variable capital X. Okay, so our goal was to calculate probability of an event, and now we'll do that using the random variable by interpreting the events or connecting the events in terms of random variables. Okay, so now so the question is now, how do I calculate probability of events? And this is where we'll define what is called the probability mass function or the probability density function of the random variable. Okay, so what is the probability? So which will characterize of my random variable? Probability density. Density is a very general term. Density will also use for continuous, but for discrete case, discrete random variable, some people will also call it a mass function. So probability mass function corresponding to a random variable. How we define it? Simple, very simple. So let Rx, okay, be the range set of X. So we have a random variable in the picture first of all. Then we have a range set, okay, of a random variable X. Then again, this function Rx to R defined by this Fx equal to probability of, now see X equal to X. I'll just write this. So what okay, I'll come back what it means. It's just probability of this particular event, X equal to X. This is called the PDF. The PDF means probability density function, or PMF, probability mass function of X. So what did it start with? we had this sample space S. This is my real line R. I pick any point X. Then I define my event X equal to X. That means all those points here, given any X. This is for any X in the range set, okay, where it is mapped to. Even if you do not take a range set, then that will be just a null. This will be just an empty set, doesn't matter. So if you take any X, then I'll have the corresponding event here, which is nothing but set of all sample points which are mapped to this. Then I'll calculate the probability of that event. I'm declaring this as a function of X, small x. This X is what? This is a real line. This is a real number, okay? And then this function will characterize the properties of this random variable, and it is known as the PDF of the random variable. Okay, so I have actually three things here. One is my sample space, S, then this real line, and then this is from 0 to 1. This interval probability, 0 to 1. I first take X here, then I go back here, I'll get an event. Now from this event, I'm calculating the probability, which is here. This is P of A. I can say P of AX. AX is the event corresponding to small x. So everything depends on this small x now. And so I'm declaring this as a function of x. So this depends, this probability P of capital X equal to small x depends on the small x. So it is the probability mass function. So it is the probability density function. It is defined for the range set of the random variable, or I can take any real number from here, any real number. If it is not in the range space, then the corresponding event will be, of course, null set. So we have probability 0 there. Okay, so that is not contributing anything to positive probability. So just let us see an example. So let us see an example means we'll define a discrete random variable, and then we try to calculate what is this function. Okay, the function, the probability density function corresponding to this random variable. So let us see an example. In fact, you will see a little later that nothing matters. If you know this PDF, that is enough to calculate everything about this random experiment. Everything will boil down to this PDF only. And this will play the fundamental role actually. But PDF corresponding to a random variable, the way you have defined the random variable. In fact, you can of course say, I'll take any function fx. Here, what we are talking about? We first define a random variable, then we define this event, and then I am saying probability of this event is this value f of x. That is how you can calculate f of x. So if I start with a random variable capital X, then I can find this value f of small x. But I can do the reverse also, and that will be actually the question. If I give you any function f of x, let's say f of small x, let's say this is defined on the real line, then does there exist a random variable for which this will be a PDF? And if that is the case, then what kind of random experiment this PDF can explain? Then that will be the question. We'll deal with that a little later, maybe next day. But let us see some example. Okay, let's say, suppose we have a box. We have a box that contains 2 black balls and 3 white balls. Okay. Now you start picking the balls from the box without replacement. Okay. Now start. Okay. Start picking the balls. This is my experiment. Balls. Okay. From the box. From the box, not together, but successively. Pick the first one, then the second one, then the third one, then the fourth one, then the fifth one, because it has only 5 balls, 3 plus 2. Successively and without replacement. Otherwise, this process will go forever. Without replacement. Now, suppose I define my random variable. Let's say, suppose the random variable, it has to measure something with respect to the sample points. A random variable x is the number of draws. Draws means you're picking the ball. Number of picks also you can say. Number of picks until the last black ball is obtained. Now question is, find the probability or the PDF or density function of probability mass function of x. Okay. So what is my sample space? That is the first question. Okay, what is my sample space? Now let's try to see here how the random variable is defined. Random variable is the number of picks until the last ball is obtained, last black ball is obtained, and there are only 2 black balls. So the process stops whenever you receive the last ball, whenever you obtain the last ball. So we are starting the experiment here. And we have how many? 3 white balls and 2 black balls. Now, once you pick the first time, 2 things can happen. Either you can get the black ball or you can get the white ball. Okay. Then again, you have to pick because you did not get the last ball. Okay. Suppose this happens that you got the black ball. And again, you have to draw another ball because you did not get the last ball. And again, 2 things can happen. That you got the black ball or you got the white ball. Now, if you get the black ball, then your experiment stops because you got all the black balls, the last black ball. But if you get white, then again you have to draw a ball. Again, you may get either black or white. If you again get white, again you have to draw because you did not get the second black ball. Again, if you get the white, then again you have to draw, and here it will stop because you have withdrawn all the white balls because there are 3 white balls, and this is the last option. Then you have to get the black ball, the remaining last ball here. Same thing you can do here. Suppose the first ball was white, then you can have 2 options, either to get a black ball or to get a white ball. Once you get a black ball, first time you got the black ball, so again you have to draw and get a black ball. You can get a white ball, and again you can get a black ball or you can get a white ball, and then at the last you will get a black ball here because this 3 white ball is saturated. Now, if first 2 times are white, then again you can draw a black ball and a white ball, black ball and the white ball. And if you get the black ball, this is the first time you got the black ball. Again, you have to draw. Either you get black or you get white. But if you get white, if you get black, you will stop. But if you get white, then there is only 1 ball left. And the next try, you'll get this black. And if you get white here, then here definitely you get the first black because there are only 2 balls remaining, first ball and the second ball. Okay, so this is the entire experiment. So what is the sample space here? Until you get the last black ball means the sample space here is like this. These are all the possibilities here. Either you'll get both the black balls in 2 draws. So like this scenario. Okay, or you'll get black first, then W, then black. So this scenario. Okay, the otherwise you get black, white, then black, white, then black. Or you get the white, then black, then white, then black. So you'll get all those things, and finally you'll get this, the last one here. Okay, this if you could have followed this path, then it is W, 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 B, B. Okay, so this is your sample space. These are the possible outcomes here. Okay, that either you have first 2 times black balls, or you have black, white, black, black, white, white, black, and so on. So this is the sample space. And how many points are there in the sample space? So in the sample space, how many points are there? You can check. This will be 10. Okay. And you can also see what is my random variable x, how it is defined. Okay, let us see. This is my sample space. Okay, I have B, so this is 1 point, BB. Then I have BWB. Then I have WBB. All this BWWB. WB. I mean, you can write it in any sequence. So you only have to finish that where both the balls, black balls, are obtained there. So you keep on doing this. And then you have this real line here. I can also draw a vertical line for this. This is my real line. And this is my sample space. Okay, sample space is 10 points. And then what is my random variable? How do I assign this numbers to this balls? Is a number of draws, the number of picks. So how many times it is picked? 2 times. So I have to assign 2 for this. Okay. Here, both cases I have 3. So I have 3. The value is 3. Okay. And here, for example, the last one is like WWWBB. For example, here I have to have 5. And here or here, similarly, I'll have 4. And the remaining sample points you can take. And this is how I'll get my how I'll get my random variable x. There's a number of picks to get all the black balls. Now, what was my fx? X could be in the range space, which is 2, 3, 4, 5 here. Now, fx means what? Probability of x equal to small x. So what is the event here? If x equal to 2, so f of 2 is what? F of 2 is probability of x equal to 2. And this will be probability of this event. X equal to 2 means what? There is only one event. Okay. Here we assume that they are randomly selected because there is no probability assigned to it. So it is the number of elements here. So it will be 1 by 10 because S contains 10 elements. Similarly, we can find out f of 3, which is probability of x equal to 3. So you'll find out probability of some events. Some event here. Here is like, for example, then this is here BWB, WBB, BWB, WBB. And in fact, these are the 2 possibilities because you can have 2 balls, 2 black balls. These are the only possibility. The probability will be 2 by 10. Similarly, you can have 4, f of 4, which is probability of x equal to 4. And you can have all the possibilities. X equal to, from it could be WWBB, for example, or BWWB, and so on. You can have WB, WB, okay, or you can have WW. Oh, I already have written WB. Okay, yeah. So any more element here? I think it is exhausted. Yeah. So this, then you have probability 3 by 10, and similarly the remaining must be the 5. So which is 3, 2, 5, 6. So this is 4. This will be 4 by 10. Okay. So you can find it out. What is this? Probability of x equal to 5, and you will see there that there will be 5 elements, 4 elements. So here ultimately we'll have 4 by 10. So I got my function, a PDF of the PMF corresponding to this random variable. Okay, and this is called the PMF. So now, okay, we are running out of time. So the thing is, what we did today here, we first talked about random variable, then we talked about discrete random variable, then we talked about probability density function. And we'll see some more examples next day. And then we'll see what are the properties one function should have so that it can be treated as a probability density function of some random variable. Okay. I may not know what is the random variable also. Okay. Suppose I am having some surface, some kind of a curve, which I am assuming that this could be a PDF. Then the question will be because of some context. And then the question will be, what is the corresponding random variable? Okay. Or what are the properties of that random variable? What are the events? And I want to calculate the probabilities of the events or all possible events corresponding to that PDF. Okay. So yeah, we'll be talking about that next day. So I'll stop it here. We're running out of time. If you have any question, you can ask me.
Can you tell the solution of the whatever question you gave last day in homework?